All right. Welcome to Friday, day 10. Last elevate, raise your hands. Woo, congratulations. All right. Congratulations, guys. All right. Today, we're going to go over some aircraft systems, but first and foremost, my name is Mark Lynn. I will be your instructor for today. We got pretty much this pretty lengthy lesson, so I will do my best to try to get this done in a timely fashion, but without leaving you guys super confused, right? So first and foremost, the sign-in link is in the chat. Let's get that out the way. Then we're going to go over aircraft systems. Am I sharing the wrong screen? Okay. We're going to go over airplane systems. Just remind me again, and I haven't done private in a while. Did you guys touch on any aircraft systems so far, like pitot-static, electrical, fuel, anything like that? Not really? Yes?
We did
Okay.
touch on some of them a little bit.
Okay. But you did touch on like VORs, right? Or no? See some people saying yes, some people saying no. Okay. So first one is a lengthy one. I'll probably have to give you guys a break in between. But once again, at any point in time, if you have any questions, please ask. All right. But let's try to get through this in a timely fashion, but without you guys feeling like, what the heck did I just learn, right? So welcome. It's day 10. It's Friday, right? Even if this is not your last class, guess what? We got the weekend off, right? So glass half full. All right, no to VOR, pitot-static, yes, a little bit. Great. All right, airplane systems, right? We're going to look at our primary and secondary flight controls, and we're going to look at some de-icing and anti-icing equipment, as well as our power plant being our engine and our propeller, our landing gear system, fuel, oil, and hydraulic systems, electrical, avionics, pitot-static, vacuum pressure, and associated flight instruments, and in our environmental systems, right? Just quick show of hands, if you guys are covered it. Vacuum system? No? Yes? I see some confused faces. Okay. So, but we definitely said a little bit on VORs.
I think based on the videos that were required for today's lesson that we had to watch before, we've
Right.
covered a lot of them, but very little. So I
Okay.
feel like this kind of just brings everything together.
Right. Okay. I just want to make sure that, you know, it's not like a first introduction, but you touched a few and it was quick. Okay. Like I said, I'm going to try my best to go through this without skipping. Not without skipping, but without leaving you guys, you know, super confused. We're going to go a little bit more in depth into it and get that going. But once again, if you have any questions, please raise your hand. Let me know. Reminder, please make sure you have your cameras on and available. And all right. Like I said, cameras on front and center, ready to learn. All right. This is the last day. I would hate for you not to receive credit for today. So, primary and secondary flight controls. All right. We have primary controls, which are our basic flight controls that are needed for flight. Okay. That would include our ailerons, our elevator, and our rudder, right? Those are the those are the minimum control surfaces that we need in order to have full control of the aircraft. How many people we have in here? We have 35, 38, so I should be missing about 32 people. All right, does anybody in here that's just auditing and doesn't need to sign in or out? All right, sorry, quick attendance real quick. Is it Freya? Are you here? Okay, so everybody else is signed in. All right, sorry about that, guys. Just trying to make sure everybody's good and ready to go. All right, so primary flight controls. We have our ailerons, elevator, and rudder. Those are required for operation, all right? That is going to control the movement of our aircraft around our pitch axes, our roll axis, and our yaw axis, all right? So if we look, we have 3 axes. Front to back, that would be our roll axis. That controls our roll, right? Side to side, kind of think of it through the wings, that would be our pitch, up and down. And then yaw would be our vertical. So if we go top through the bottom, kind of like this, you guys can see my pen, right? That would be our yaw. Okay, so our ailerons control roll, elevators pitch, and rudder controls yaw. Anything else is secondary, right? So we have our flaps, any leading edge devices, spoilers, and our trim tab. All of our secondary devices, they improve performance, okay? So primary, required for flight, secondary, improve performance. Got that? Cool. So the airplane itself, it exists in 3 dimensions, like I said, roll, pitch, and yaw. So movement about the axis that runs nose to tail is our roll. Movement around the axis that runs wingtip to wingtip is our pitch. And then movement around the axis that runs from belly to back is called yaw, okay? So we had a pole going through the aircraft and it would rotate around each respective axis, all right? Not all 3 at once, but if we had one individually, one of those 3, then that would control our movement. So when elevator, ailerons, we have the 3 axes that they operate on, but the more airflow that we have going over our control surfaces, the more effective our input is, okay? So basically, the faster that we can move through the air, the more effective our inputs of the controls will be, all right? When you guys get to practicing your maneuvers, you're gonna practice slow flight, right? Slow flight, you configure the plane with flaps, so that way you can add more lift, but fly the airplane at a slower airspeed. And you'll get to experience what the controls feel like when you're moving at a slower airspeed. The controls will feel mushy, they'll be less responsive, right? That is where you get an idea of what it's like, and it's also gonna help you when you're learning to land, because what do? As we come into land, we slow down our speed, right? We slow down our speed and our control inputs are going to get less effective. So ailerons controls movement around the roll axes, right? In the cockpit, we turn the yoke to the right in order to let the plane roll to the right. We turn the plane to the left, the yoke to the left, the plane rolls to the left. But how does it do that? Well, one of these ailerons is going to deflect upwards, right? So if we look at it from a side view, one of the ailerons will point up like this. I don't know if can you guys see that? I know it's kind of blending in, right? If we look at it more so from this perspective. So one of the ailerons will go up while the other goes down, right? So this one is down, and then this one is up. What is that going to do? That's going to create extra force pushing up on this wing and less pushing up on this wing, which allows it to roll. Okay? So if we look in this diagram we have on screen here, we have greater force on the left because that left aileron is down, and less of an upward force on the right, which is going to allow the plane to roll. Questions? Can I get a thumbs up if everybody gets it? All righty, cool. I'm gonna ask you guys that a lot because, like I said, I can't know what you're understanding. If I'm not talking in layman's terms, let me know. All right, it's hard for us as pilots to speak in layman terms sometimes. So bear with me. So when we look at the ailerons again, when we have equal lift on both wings, we are level flight, right? But once we change that camber or the angle of that aileron, we're going to generate more lift on the side that is down, less lift on the side that is with the aileron up, which is going to push the aircraft around that roll axis in an upward position. That's going to cause us to turn. All right. So more camber, greater angle, more lift. Less camber, lesser angle, less lift. Okay. And that is how we turn the aircraft. But we do have a consequence of that. Okay. We have something called adverse yaw. So adverse yaw is a consequence of lift is drag. So as we generate more lift on this, with this aileron down, we're generating more lift so that we can bank to the left, right? We're also creating more drag. In comparison to this side, we have less lift, so therefore we have less drag, right? That is going to cause the aircraft to want to yaw, right? It's going to want to yaw. So you're going to have a force felt on this side. As more lift is being created, that's going to cause the aircraft to want to yaw in that direction. Okay? So more lift, pushing the wing up on this side, also creating more drag, pulling the wing like that. Okay? What that's going to do, I mean, what we have to do now is this is where we have to incorporate our rudders, right? Because all the rudder is another control surface that can deflect, right? So we have that adverse yaw. When we push rudder pressure in, it changes the control surface on the rudder, and it allows us to have the plane regain coordination, and that is what a coordinated turn is, right? When we're not in a slip or a skid, we have coordination because we're using the rudder to help keep us coordinated and to reduce that adverse yaw, right? Let's look at it from here. As the rudder deflects to the left, that force is going to be felt going sideways this way, and that is going to point the nose to the left. So if we push left rudder, the nose points to the left. If we push right rudder, the nose points to the right. Okay, so we're trying to counteract that adverse yaw. Questions? You sure? All right. So every time we turn, We push the rudder in the direction of the turn so that way we can stay coordinated and reduce the effects of that adverse yaw or that drag that is now pulling one of our wings backwards, right? Another way that we counteract that is not just with the rudders, but we also have a design that the aircraft engineers have come up with, and we call it differential ailerons. Okay, that simply means that the aileron that goes down in order to generate more lift, right, is not going to deflect at the same angle as the aileron that goes up, right? So it's still deflecting downwards, so that way we could generate enough lift to lift that wing, right? We generate enough lift to lift that wing, but not as much as the opposite one. That's going to do what? If we're not generating as much lift, what's that going to do with the drag? Yep, it's going to lessen the drag, right? So if it lessens the drag, the amount of adverse yaw or force that is felt pushing the nose that way is going to be reduced. Okay. So one aileron raises a greater distance than the other is lowered, right? So that is a differential aileron. Now we also have what you call a freeze type aileron. That wing that is going upward, right? So we're in the turn. We have drag creating adverse yaw. We use the rudder to reduce that. Then we change the angle of deflection downward. That reduces that even more. But then now on the upwing, on the up aileron with the down wing, if we look at this diagram, we have a freeze aileron. That is going to expose the bottom portion of that aileron to the airflow. So if it exposes the bottom portion to the airflow, what is that airflow going to do with that aileron? Anybody take a guess?
It's going to catch there and move up, take the path of least resistance to the lower pressure.
Okay, that's an extensive way to explain it, but simply is going to hit that surface and then create more drag, right? We have that airflow moving from here, it's going to hit that, and it's going to create more drag, right, Caitlin, Ashley? Right? So what is that now going to do to the effects of the adverse yaw that we're feeling? It's going to create a little bit more drag here and add some force on this wing and pull the aircraft and reduce the amount of adverse yaw that we have to combat with the rudder. Questions? I see everybody's face. So we have differential ailerons. The deflection is not equal from up aileron to down aileron. Then we have freeze type, which allows some airflow to hit the bottom portion of that up aileron, right? Creating a little bit more drag for us on the opposite wing. On the Archers, we only have differential ailerons. We do not have freeze type. So as the airflow goes underneath here, it does not hit this bottom portion. On the Cessnas, we have differential and freeze type, right? It has a mild freeze type design. So a little bit of that airflow is going to hit this bottom portion here with the up aileron. So remember, the up aileron allows the wing to dip down. The down aileron allows the wing to lift up. Does everybody follow that concept? Yeah? Cool, good. Now, let's look at our elevator. Right? So in our elevator, it controls around our pitch. In the cockpit, if we want to pitch up, we pull back on the yoke. We want to pitch down, we push forward on the yoke, right? Well, just like with the rudders, just like with the ailerons, we are deflecting one of the control surfaces. If we deflect the control surface upward like this, then it's going to create more force and create a downforce on the tail, right? Creates a downforce on the tail, which then pitches the nose up. If it goes in an opposite direction, the elevator is pointing down, it's going to create an upward force, which pitches the nose down. Okay? So as it goes up, it pitches down. It goes down, it pitches up. Okay? All of these control surfaces act as an airfoil, right? So all of it, just like the wings, is generating lift with the airflow going over it, and we're just manipulating how that air interacts with those airfoils. And that results in control of roll, pitch, or yaw. All right, so here we have our secondary flight controls. The secondary flight controls do what again? Do we need them for flight? No, but we want to improve the characteristics, right? So we have wing flaps. We deploy the flaps. You see them on airliners like here and on the Cessna. We have trim. So we have a trim tab that allows us to fine tune and adjust or relieve control pressures on the yoke. We also have spoilers, right? And I mean, people have been on the airline and when you land, you see these spoilers come up, right? Or you also have leading edge devices like these slats, right? On the airliners, we have those movable, they have those movable slats on the front edge that move forward, right? All of those are secondary flight controls. They're not needed, but they improve the characteristics based on what we needed to do. So let's look at some flap designs. Flaps increase lift and also induce drag, all right? One thing I want you to know is that anytime we generate lift on our aircraft, induced drag is a byproduct of that, okay? So if we're increasing lift by using our flaps, we will also increase drag. Here we have a plane flap where it's basically hinged to the aft portion or the back portion of the aileron, of the airfoil, excuse me, of the airfoil. And when we put them into position, they just angle downward. Then we have a split flap. Split flap is hinged on the bottom portion, but it's not interfering with the top portion. And when they're retracted, they just sit up. When we deploy them, they float down. Slotted flaps. These are probably the most common, right? It has an open slot here that adds energy to the wings boundary layer and produces less drag. All right, these are what you will see on the Archers and on the Cessnas, slotted flaps. Then we have Fowler flaps. Fowler flaps are like slotted flaps in the fact that they allow the airflow to go in between, as these arrows depict, but they also move backwards. If they move backward, it both changes the camber, the angle, and it also changes the chord, so it makes the wing or the airfoil longer. Okay, so they slide back into position. The slotted flaps just go from a level position down into an angle position with the gap in between to allow air to flow through. Okay. So to pretty much summarize that, any type of flap configuration is gonna do what? It's gonna do two things. Somebody give it to me.
Increase lift and induce drag.
It's gonna increase lift and increase the induced drag. Right? So that's gonna allow us to fly at slower airspeeds. Right? That's why we use flaps on landing. Because we want to come into land, we want to fly at as slow of an airspeed as we can to allow those wheels to touch down gently. Okay. Any questions on flaps? Now here we have another secondary control is our trim tab, right? Also kind of known as a poor man's autopilot. Its job is to reduce the workload on the pilot. So when we get to cruise and level flight, we can use our trim tab to help release those control pressures. Right? If we're pushing too much forward on the yoke in order to stay in straight and level flight, then we use the trim tab to trim the nose downward. If we have to hold back pressure and pull the yoke back toward us, we use the trim tab to trim the plane in more of an upward position. Right? So this is an example of a Cessna trim tab. This is an example of an anti-servo tab and a stabilator. All right, these are the Archers. The Archers use what we call a stabilator and not necessarily an elevator with an anti-servo tab. Cessnas have an elevator with a elevator trim tab. Okay. The big difference here is that not just that it's a larger trim tab surface, but the anti-servo tab, it moves with the elevator. So if you're moving the yoke back and forth, this is going to move with it. With the Cessnas, if you move the elevator back and forth, whatever trim setting you have this on, that is where it's going to stay until you adjust it. Right? So if we roll the trim wheel with a nose up position, that's usually rolling it upwards, right? The tab is going to move in the opposite direction. It's going to move down. Okay? So for nose up, the tab will move down. And then for nose down, this tab moves up. Okay? So remember I said the elevator controls, if we want to go nose up, the elevator is going to flip up, right? The trim tab moves in the opposite direction, right? With the anti-servo tab, an anti-servo tab moves in the direction of the stabilator and reduces the control effectiveness, right? So if it reduces that control effectiveness of the stabilator, it lessens the tendency to over control the aircraft, of putting too much elevator input in and out. Okay. So if you have a certain amount of input in the yoke with the stabilator and the anti-servo tab reduces that input. So that way you're not likely to over control and have the plane, fighting it in order to hold an altitude. All right. Anti-servo tabs are similar to balance tabs, but they move in the opposite direction. So for example, when your elevator or stabilator moves up, right, the anti-servo tab moves in the same direction. Okay. Even though it reduces the control effectiveness, it increases the aircraft control feel in small aircraft and just prevents that over controlling. Right. Everybody understands what I mean by over controlling, where you're just putting too much input in, right? Let me see something here. So like, so I could kind of make sure everybody's on the same page. All right. So that's the elevated trim tab, the anti-servo tab. Now we also have here a ground adjustable rudder trim tab. It's called ground adjustable because this is not meant to be messed with. All right, a mechanic would come and set this trim tab and they bend it in a certain direction and that's it. Right, you don't want to go pre-flight your Cessna and see that, oh, it's bent to the left and think it's supposed to be straight, and then you go to try to bend it back. No, right, it's set like that on purpose. So it's still a trim device, but we just don't have any control over it, any adjustable control over it while we're flying. The mechanic sets that, they set it and forget it. Yes, Kyle.
So there's a correct set position for that?
Yeah.
Okay.
How the process works, I don't know. That's an A&P question. But they have a way of setting this in a correct position for the aircraft and then leaving it at that.
Okay.
Yep. All right, before we go into the engine, any other questions in terms of our secondary control system? All right. So engine, power plant, and propeller, right? We're going to talk about the power plant. It's basically our engine. It converts chemical energy, i.e. gas or fuel, 100 low lead, into mechanical energy. That mechanical energy rotates and it rotates the propeller so the propeller could generate thrust, pull us forward through the air. And this is done with small controlled explosions that generate power, all right? Much like what you see in your car engines that generate power for us to be able to drive the cars, this generates power in order to rotate the propeller. So it's a 4-step process: intake, compression, combustion, and exhaust. It all happens within each cylinder. We have one cylinder here, 2, and then another 2 on the opposite side. So inside the cylinder, we have spark plugs, we have the cylinder itself, and then we have a piston. That piston moves up and down in order to compress air and fuel mixture, and then that mini combustion happens and pushes the piston back down, right? Then we have spark plugs that are connected to the cylinder. That is what creates our spark. The spark gets electricity from the magnetos. The magnetos rotate and generate the spark based on the engine rotating. Okay, so it's independent from our electrical system and our battery system. We also have here some piston rings that go around the piston, and those kind of expand a little bit. They kind of have a little bit of elasticity in them, and they will expand in order to create a seal between the cylinder wall and the piston itself, so that way any air that gets put into here cannot escape. It also uses some oil to lubricate, cool, and to seal that gap in between the cylinder wall and the piston. All right, and that's going to maintain a pressurized cylinder for our engine to work correctly. So that piston is connected to a connecting rod. That connecting rod is connected to the crankshaft, right? I want you guys to think about when you're riding a bike, right? You have your foot on one pedal and your foot on the other, right? Then you have those rods in between. Think of your pedals as your piston. The two rods are your connecting rod. As you transfer motion, what are we doing? We're creating that rotational motion, right? The same thing happens within the engine, because within the engine, we'll have one piston connected to the crankshaft here, and then you can have another piston connected to the crankshaft there, and it's creating that up and down motion using the combustion to power each side. So when it creates that up and down motion, the intake valve on one side will open, that will draw air into the cylinder. It will draw air and mix that with fuel, and then it'll create a spark that will cause the explosion to happen. Once that explosion happens, it pushes that piston down, and the other piston goes up. And they're constantly on opposite sides of the same compression, intake, compression, combustion, and exhaust. That is going to keep that same bicycle motion that I was telling you about. It's going to keep that going, and then the crankshaft continues to rotate, which then turns our propeller. As I said, our magnetos are small generators. Think of them as small generators, right? So as the engine rotates our magnetos, they're going to generate electricity that sends that electricity to our spark plugs. We have 2 of them per cylinder, right? So if we have 2 of them per cylinder, it's for redundancy. Same reason why we have 2 magnetos, for redundancy. In case one fails, we still have a backup. So each cylinder has 2 spark plugs. We have 2 magnetos, and one of them powers one set of spark plugs, and the other one powers the other set of spark plugs. Good. So here's another diagram of it. We have the 1, 2, 3, 4 cylinders. We have 1, 2, 3, 4 spark plugs. The other 4 spark plugs are on the underside of the engine. Okay. Then we have our 2 magnetos, one here and one here. Both of them rotating off of the engine power and generating spark for that combustion to happen inside the cylinder. As it creates, we have a piston inside this cylinder, a piston inside this cylinder, and as that combustion and those 4 strokes happen, it's constantly moving back and forth, just like on a bike, on both sides, and allowing the crankshaft to rotate, which then rotates this hub or this flywheel right here, and that connects to the propeller. Okay. Don't worry, I'm not leaving you guys hanging just yet. So let's look at those 4 strokes a little bit more in depth here. Intake valve opens. That brings in the air and fuel mixture into the combustion chamber. That piston is now, as that piston is moving down, it's drawing that air inside and that fuel inside. And here goes the connecting rod, and the crankshaft is rotating in a clockwise direction. As that crankshaft rotates, it's going to push that piston back up, and it's going to compress that air and fuel mixture. That, in combination with the valves being closed, is going to compress the air. With the valves, both of them closed, the intake and exhaust, a spark ignites that air fuel mixture, boom, creates an explosion, pushes that piston back down for it to rotate around once again. And then once it rotates to the down position, the crankshaft is going to push that piston back up, and the exhaust valve is going to open, allowing the exhaust gas to escape. Then it reaches that top position and then it goes back and starts all over again. Right? Here's a graphic of this working. So here we have air coming in, it's being drawn in, compress, explosion, and then release. Drawn in, compress, explosion, and then released. Okay? So this is intake, this is compression, this is combustion, and then this is exhaust. Yes, Joshua, that is another way to remember it. All right. Manuel. You gotta unmute yourself.
What are the two rotating pins on top of the intake outtake valves?
Right here?
Yeah.
These are camshafts. So when they rotate, they basically open and close those valves, allowing the air to either be drawn in or to escape.
Are they timed with the crankshaft as well?
Yes. Yeah, they work in a specific timing along with the magneto, so that way everything happens right when it's supposed to.
Got it.
Yeah. Good question. All right, how are we feeling about the basics of that? What are the three things we need for the engine to run? We need three things.
Air, fuel, and oil, or
Well, air, fuel, and spark, right? Because we need something to cause that combustion to happen, right? So we need air, fuel, and spark. All right. Now we do need oil, because if we don't run oil, then the engine can seize up. It can friction can cause it to get too hot, all that stuff. But that's a separate topic. This is what it kind of looks like, similar to that bicycle action, right? Right? How are we feeling? We got the basics. Trust me, you guys don't have to be mechanics, right? You don't have to be mechanics about it, but just know we need those four things. We have the 4 cycles, which is intake, compression, combustion, and exhaust. And then we need 3 things for the engine to run: air, fuel, and spark. Okay? Same things that your car needs. Write this acronym down, LHAN. Right? This describes the engines that we have in our Cessnas and our Archers. So LHAN, L is for Lycoming. Lycoming is just simply the name of the company that makes the engine. Okay? H is for horizontally opposed. Okay? Just like in this diagram, we have the cylinders that are horizontal to each other. Right? They go in a horizontal plane. Air cooled. As air flows through the inlets in the front of the aircraft, it runs through these fins on the side and it helps cool the engine down. Okay? Our cars, they're liquid cool, right? We have to put antifreeze or coolant into our cars and it helps cool it down. We don't have that. It uses the airflow as we fly through the air to cool it down. Naturally aspirated, just meaning that it's basically breathing its own air. It doesn't have anything that's compressing and forcing air into the engine for us, right? Like a turbocharger or a supercharger, if you ever heard those terms before, right? And then direct driven, meaning that the propeller is directly connected to the crankshaft. Okay? There's nothing in between the propeller and the crankshaft for the rotation. Okay? Give me a thumbs up if you're feeling good. Raise your hand if you have a question. All right. Trying to make sure you guys ain't just trying to get out of here. Just tell me that you got it. All right. So remember I said that our control surfaces, our primary control surfaces, our flaps, they're airfoils, right? They all generate lift. Well, guess what? The propeller is an airfoil as well, right? Except that instead of us generating lift in a up or down direction or even a side to side with the rudder, we're generating lift that's pushing backwards, right? Just like a fan. Think of it like a big fan blade, right? So it's at a certain angle, has a certain angle of attack that allows it to generate lift. And that lift we call thrust. That's what moves us forward through the air. So it's pushing that air backwards. Okay? We have two types. We have a fixed pitch propeller. A fixed pitch meaning that it has an average performance. The angle of those propeller blades cannot be changed. All right? Then we have others are called pilot adjustable, or they're pilot adjustable to optimize performance. So if you hear anything about a constant speed propeller or adjustable pitch propeller, that means that we have control over that pitch in order to change the performance characteristics of it. But on the Cessnas and the Archers, we have a fixed pitch propeller. We have no control over the angle. It's going to allow us to climb, and it's going to give us an average performance for climb and an average performance for cruise. All right. Sometimes you can have propellers that are specifically designed for climbing, but they suffer in the cruise department, right? Or they might be built for cruise, but they suffer in the climb department. Right? It all depends on what you need for your aircraft. Okay? Yes, Manuel.
I know you might explain this later on, but what's the whole ordeal with manifold pressure in adjustables?
So manifold pressure is just a way to measure power output, kind of like your RPMs, but because with the adjustable propellers, adjustable propellers are designed to keep the engine rotating at a certain revolutions per minute. Okay? So when you adjust the throttle now, you're measuring that using your manifold pressure. But that's only with the adjustable pitch. Right?
Okay.
Fixed pitch, we just use RPMs.
So it's the same concept, just a different naming.
Yes, it's a different naming. With the adjustable pitch, you're using manifold pressure and RPMs, but you're setting it to a certain RPMs that you want using the adjustment of the blade angles of the propeller. And then no matter what you do with the throttle, it's going to constantly adjust to keep it set at that same RPMs. So it keeps rotating at the same speed. Okay, it's just changing the blade of it is going to change the amount of thrust that you can generate.
Gotcha.
Even though it's rotating at the same speed. Any other questions? All right. You don't have to worry about too much about adjustable pitch propellers yet. That really won't come into play until you get to multi, right? So don't get too caught up on that. All right. Our electrical system. It supplies electricity to our avionics, our radios, our lights, and sometimes flaps. Why do I say sometimes flats? Anybody know?
Does aren't
Archers-
like the bigger planes have electronic flaps?
Yeah, but even more so, some of us might be flying Cessnas, some of us might be flying Archers, right? In the Cessna, we use an electric motor to extend and retract our flaps. In the Archer, we have that bar that we lift up and down, and it's mechanically linked, so we don't need electricity to set the flaps in the Archer, but we need them for the Cessna. So that's why I say sometimes flaps. Okay. So, some components of the electrical system will be our alternator. Just like the car alternator in your car, it rotates off of the engine power and generates electricity. Okay. Then we have the battery. Just like a battery in your car, is going to store electrical power for us, right? For us to use when we need to start the aircraft before the engine is running. Then we have a master or battery switch that is going to send it's going to turn on the electrical system, right? Turn it on or turn it off. Then next to the battery switch, we have an alternator switch. That is going to allow us to turn off the alternator in the event that we have a alternator failure, right? So if the alternator fails, we could turn off the alternator, we could leave the battery switch on, and that'll allow us to use the battery power for a limited time until the power runs out of that battery. All right. Then we have a bus bar. So we have a primary bus and an avionics bus that distributes the electrical power to various components of the aircraft. Then in between that, we have circuit breakers. All right. If too much electrical current is going to one of these items without the circuit breakers, then it can damage that item. But the circuit breaker's job is that if there's too much current going there, then it will pop the circuit breaker. Right? Anybody else has ever had the lights go out in their house and you have to go to the circuit breaker and reset it? Same concept. Right? Same concept. Voltage regulators. So we have some voltage regulators that their job is to regulate the amount of voltage that charges the battery, and it stabilizes the electrical output that's coming from the alternator. Right? That is going to keep the electrical flow consistent, so we can have power that charges the battery and power that charges the rest of our electronics. Then we have here an ammeter. The ammeter's job is to show whether we have a overcharge or a discharge in electrical power. So if the alternator was not putting out enough power to recharge the battery, we would see a discharge, and that'll let us know that the alternator is not recharging the battery and all the power is being drawn from the battery. That would be a first sign that we have an alternator failure. Right? On the contrary, if it was on the high side, that'll let us know that maybe the voltage regulators are not working. The alternator is putting out too much power and it could damage our electronics. Okay? So think about the alternator power coming out. It's kind of like Goldilocks, right? It can't be too hot or too cold. It has to be just right. Okay? If we have a load meter differs in the ammeter in the sense that it's just measuring how much current or how much use is being put on, how much stress is being put on the electrical system. Okay. So it's how much load is being placed on that electrical system, mainly the alternator. Quick facts about the electrical system on the Cessna versus the Archer. They are both 28-volt systems, right? and they both use a 24-volt battery, right? In order for us to recharge the battery as the alternator is producing electricity, we need a higher voltage system than we do a battery. So that is going to allow us to recharge that battery up to 24 volts, but still use excess in order to power our electronics. Right? The only difference between the Cessna and the Archer is that the Cessna uses a 60 amp alternator and the Archer uses a 70 amp alternator. But they are both 28-volt systems with 24-volt batteries. And having that extra voltage allows us to recharge the battery and power our electronics as the engine is running. Okay. Any questions with the electrical system? Yeah, Manuel?
Which one has an ammeter and which one has a load meter? Or both have
The Cessna has an ammeter, right? The Cessna definitely has an ammeter. The Archers, I want to say it's an ammeter as well. I'm not too sure. I trained in the Cessnas. But in Archer, yeah, the Archers I believe might have an ammeter because in the Archers, if you lose your alternator, it's going to show a 0 indication versus a negative, right? So remember I said the ammeter will show negative or positive charge or right in the middle. Load meter is going to show 0 or it's going to show a load.
So Archers may have a load meter.
Yeah, it may have a load meter.
Sorry, what did you say? Yeah, so 24-volt battery and then amp alternator. What is the 28-volt system again?
So when the
system.
alternator is spinning, right, it's going to generate electricity up to 28 volts. Okay, that 28 volts, having that extra 4 volts is going to allow the battery to be recharged and power our electronics simultaneously.
Got it.
Yeah.
Thank you.
Any other questions? All right. The ignition system. This is how we get the plane started, right? So we use battery power to trigger the starter. The starter is going to spin this flywheel, all right? The starter has some gears along here, and it has some gears along that flywheel. That flywheel is connected to the propeller and the crankshaft. That gets the engine rotating. Okay? Once that gets the engine rotating, it's going to rotate the magnetos. Then the magnetos power the spark plugs, and the spark plugs will ignite the fuel and air mixture.
You know, a lot of people.
Let me see real quick, just to give you guys a kind of visual of it. So it's very similar to a starter on our aircraft. This is similar to the flywheel, right? The starter has a series of gears on it that's going to rotate that flywheel. And that's going to rotate the engine. Okay. Once it rotates the flywheel, that'll rotate the crankshaft and get the moving parts going. So starter engages the flywheel, rotates that, gets the engine going. Then through this drive belt right here, this rubber belt, that's going to spin the alternator. Okay. All right, so we use the battery to power the starter. Once we have the engine running under its own power, we no longer need the starter and we no longer need the battery. Any questions? And we have the oil system, all right? The oil system is vital to our engine because it lubricates and it cools the engine, right? And it also serves as a seal. Remember I said that it lines the side of the piston and helps create a seal between the cylinder and the piston wall, right? You can have two types of oil systems. One would be a wet sump. On this engine, we have a wet sump where all the oil is contained down here, and then it gets pumped and circulate through the engine. On a dry sump, just imagine as if the oil system or the reservoir was separate from the engine. It was in a separate tank. That would be a dry sump system. And then it uses that pump to circulate and move that oil throughout the engine. All right. We need an oil pressure gauge and an oil temperature gauge. The reason why we need those is because we need to make sure that we have enough oil pressure. If we do not have enough oil pressure, it could be due to poor circulation. If we do not have oil circulating in the engine, it's not going to lubricate or cool, right? If we don't have the right temperature, if the temperature is too cold, then the oil could get too thick, right? Much like when if you cook some food and you have some oil in the food and then you put it in the fridge and it starts to get hard and solidify. Same thing, we don't need it too cold and we don't want it too hot, because if it gets too hot, then it starts to thin out and it won't perform how we need it to, right? And it won't cool down, and it won't lubricate as well. So if you ever lose oil pressure or your oil temp is way too hot, then you have an emergency. Let's look at how that flow works, right? So we have the engine and the sump. This is where the oil sits. We have a strainer here that will filter out any big particles, and the pump is pulling that oil to this point. Now this is called a thermal bypass valve, right? The thermal bypass valve is measuring the temperature of the oil. If the oil is cool, then it goes straight to the filter, which then filters out any more particles. Then it goes through a pressure relief valve that is adjusted by a mechanic, and that's going to help maintain the oil pressure and send it back to the engine to lubricate and cool the engine. But if that oil reaches the thermal bypass valve and is too hot, then it sends that oil to an oil cooler, okay? Works like the radiator in the car. The oil goes through the cooler. We have air passing over it, over the radiator to cool it down. And then it sends the oil to the filter and through the pressure relief valve and back to the engine. All right. So the purpose of the thermal bypass valve is to keep the oil at an optimal temperature. Questions? Let me see something. All right, do you guys want a quick 5 minutes before continuing, or you want to keep going? See, Diego says keep going. Somebody else says 5. Keep going, keep going. All right, raise your hand, 5 minutes. Keep going. I'm sorry, 5 minutes, guys. Go ahead. Oh, were you just raising your hand? Got you. All right. But we do still have 2 more slides after this, but this is gonna be the longest one, promise. Fuel system, we have 2 different types, fuel injected and then carburetor. Okay? So the carburetor, fuel is pushed into this fuel float chamber. Okay? This float chamber houses some fuel for us. When we adjust the mixture in the airplane, this adjusts the mixture needle, and that controls how much fuel is allowed to flow through this discharge nozzle. Okay? That fuel is then pulled in because as airflow goes through the carburetor, through the venturi, it creates an area of low pressure, and that is going to pull the fuel into the carburetor. That fuel then mixes with the air and it passes through a throttle valve. So when you push the throttle forward, we're opening the valve. When we close it for less power, it closes that valve. And that allows the air and fuel to go to the engine. Okay. So we have an area of low pressure, which is also going to pull down some of that air, as well as adding fuel in there is going to cool down that air before it goes into the engine. All right, I want you guys to remember that in a second. Because that air gets cooled down, we can experience what we call carburetor icing, right? This occurs due to the decrease in air pressure in the venturi, which causes a drop in temperature. It's most likely to occur below 70 degrees Fahrenheit and a humidity above 80%, but can occur as hot as 100 degrees Fahrenheit, right? So to combat carburetor icing, we have carburetor heat, all right? If we turn on the carburetor heat, if we suspect that we have carburetor icing, we can turn on the carburetor heat, and then we will notice a decrease, an initial decrease in our RPMs, and then a gradual increase. A gradual increase because it is removing that ice or melting it away. Right? We have an initial decrease because it is putting warm, unfiltered air into the carburetor. Right? It gets that warm, unfiltered air from the exhaust system. Takes heat and unfiltered air and puts it into the carburetor, and that will end up melting the ice. That's why we have an initial decrease, because engines don't like warm air. The colder the air is, the better the engine can perform. So once we add colder air from the engine, hot air from the engine exhaust back into here, that's why there's an initial decrease, but as it melts away that icing, the RPMs will increase. Questions with the carburetor system? Charles?
When would you suspect that you do have carburetor icing? What are like the signs to look for to know to turn that carb heat on?
If you have like a rough running engine, right, that would be one of the first signs. A loss in RPM, right? If you were cruising around like 2,300 RPM, then all of a sudden it drops down to like 1,900, and you haven't done anything, you can suspect that you probably have carburetor icing. So you pull that carb heat on and you give it a second and see if the RPMs improve. If they do, then most likely you have carburetor icing.
Roger that. Thank you.
No problem. Now, in more modern engines, like the newer Cessnas, and we'll have a fuel injection system. So fuel from a fuel tank is routed through to an electric fuel pump and an engine-driven fuel pump. That pumps fuel to a fuel air control unit, which then sends that fuel through a fuel manifold valve, which distributes that fuel to each cylinder. Now, as opposed to mixing the fuel here, it's mixing the fuel and injecting it into the cylinder. Okay? It's putting it right into the cylinder and mixing it with the air. The spark still happens and causes that combustion. Okay? So with this system, we're less susceptible to carburetor icing because we don't have the carburetor. Right? So we have no carburetor icing, but we still have impact icing. All right? That's just simply from a lot of cold air being rushed in, impacting, right? Fuel injector system can be hard to start on a hot day, and it's susceptible to vapor lock. Vapor lock is simply when the fuel gets close to a hot engine and the heat inside this fuel lines causes that liquid to turn into a gas, right? So you might have some gas right here as opposed to a liquid, and that will cause the fuel pump system is not designed to pump a gas, it's designed to pump a liquid. So then vapor lock is basically that we have a gas that's preventing the liquid from getting to the engine because now it can't push that gas forward. Okay, that's what vapor lock is. But we do have a better fuel flow through the fuel injected system, and we will control the mixture. The mixture knob inside the aircraft controls the fuel air control unit. Right, that adjusts how much fuel is put into there. Caitlin.
How do you fix vapor lock?
You honestly have to, if you have it on the ground, you kind of have to just let the engine sit. Right? If it cools back down, then the gas turns back into a liquid and it clears out.
And then when you're in the air, you just
And
let it
when
run too.
That I'm gonna look into, let you know when you're in the air. All right? When we get to our break, remind me. Gravity fed system versus fuel pump system. A gravity fed system, if you think of your Cessnas, right? The fuel tanks sit up high in the wings, and gravity helps pull it down towards the engine. Archers, they sit low in the wings, and you need an electric fuel pump to help get it to the engine. Okay? Here we have the Cessna diagram versus the Archer diagram. Once again, fuel tanks that sit up high, runs through a fuel selector valve, through a fuel reservoir, through the auxiliary pump or the electric pump, through a fuel shutoff valve that allows us to stop fuel flow at this point if we need to, and stop it from getting to the engine. Then through a fuel strainer, engine-driven fuel pump, to the fuel air control unit as in the other diagram, and then the fuel distribution valve that sends it to each cylinder. Okay. Archers are similar. The fuel goes through a fuel selector valve, through a strainer, through the electric fuel pump, then through the primer solenoid. So this is on a cold start. If you need to prime the engine, it will send fuel directly to 3 of the 4 cylinders to help get it started, right? If not, it goes through the engine-driven fuel pump, then to the carburetor. Okay. We have a fuel pressure gauge here, and we also have a fuel quantity gauge. Then we have a fuel quantity gauge on the Cessnas, but then down here we also have a fuel flow indicator. So this gives a fuel pressure indicator, this gives a fuel flow, right? It measures how much fuel is entering the system. All right. Then we have Archer and Cessna fuel systems, right? Once again, gravity fed. Cessna is 56 total fuel that it carries, but 53 is usable. Right? About 3 gallons of that is not usable. And you have 1 engine-driven fuel pump and 1 electric fuel pump. And on the newer Cessnas, we have 13 sumps. Older Cessnas have 3. The difference between Archer and Cessna now is that it has a fuel pump system, not gravity fed. 50 gallons total, 48 is usable. Both still have 1 engine driven and 1 electric fuel pump. And you have to switch the tanks. When you select which fuel you're drawing from, you can either select left or right. On the Cessna, you can have it set to both. So it's going to pull fuel from both tanks. And then the Archer also has 3 sumps. So we have 1 under this wing, 1 under this wing, and then 1 under the front cowling. Cessna has 5 under this wing, 5 under the other wing, and then 3 under the cowling. All right. Cessna used to have 3, but they realized the design flaw and found all these parts that are susceptible to have contamination like water or sediments in it. So that's why they added more fuel sumps to make sure that we don't have any contamination in our fuel system. Okay. All right. Any questions with the fuel system, guys? Am I moving too fast? All right. Take 5. It's a long slide. We're almost at the end of this one, but take 5 and come back.
You wanted me to remind you of the vapor?
Yeah.
Okay, cool.
All right. Caitlin,
Yes.
answer your question. So vapor lock is most common when you've just finished running your engine and you just shut it down. It's been sitting, it's getting hot, and you come back to start it back up again, right? So it's not as common to happen in the air because you have airflow going over the engine, cooling it down. If it does happen, in a rare occasion that it does happen while you're in the air, it's one of the tricks is to try to point the nose of the aircraft into the wind. So whichever way the wind is blowing, that'll allow more airflow to get in and to cool it down. So that way you don't have vapor lock.
Makes sense. Okay, thank you for looking that up.
But it's rare that it happens in midair. It
Got
usually
it.
happens after the engine's hot and you sit down, you shut it off and it sits. Okay,
Yes.
cool. A good question though. I like your thinking. All right. So is everybody good with the fuel system? Any other questions? All right. Aircraft will have also what we call a hydraulic system, right? The hydraulic system can be used to operate the brakes on the wheels, retractable landing gear, and some constant speed propellers or the adjustable pitch propellers. So, how that works is we have a reservoir that holds hydraulic fluid, usually some type of oil, not the same as our engine oil, but sometimes the same as our engine oil, right? That fluid is run through a pump, which is pumped into a chamber, which moves a piston down, and it uses hydraulic pressure to push that piston down. That can be used to hold up a landing gear system. That can be used to compress our brake pads over our wheel disc, or to adjust our pitch angle of our propeller blade. So the basic system will always consist of a reservoir, a pump, a filter, a selector valve, a relief valve. The relief valve is going to make sure that it does not have too much pressure, and an actuator. This will be the actuator. Okay. The most common system would be the braking system. Okay, it's not here yet. I have another diagram. But we'll come back to that in a second. But if you look here, this is our brake disc. And on either side, we have a brake pad. When we push the brake pedal, it's going to cause the brake pads on either side to compress. And that is going to stop the aircraft. That is going to help slow it down, just like on your car. We have what we call here an oleo strut. O-L-E-O. Okay, oleo strut uses a pneumatic air and oil hydraulic shock absorber. So when we are landing or we're taking off and we're rolling down the runway, it absorbs that up and down oscillation, right? Much like on your cars, we have suspensions that'll absorb those bumps and the oscillation. Very similar here. On the Archers, we have 3 of these. The 2 main landing gears and the nose wheel. They are all oleo struts. On the Cessna, we have 1 oleo strut for the nose gear, and then we have 2 tubular spring steel struts for the main landing gears on the Cessna. Right? Neither the Archer or the Cessna are retractable landing gears, right? They don't retract up into the body of the aircraft or into our wings. Only the multi-engine, the Seminole, has a retractable landing gear. Now, on the nose wheel, we have a shimmy dampener that's filled with hydraulic fluid, and it eliminates oscillations in the left-right motion, right? So it reduces any oscillations as we're rolling down the runway, moving left to right, so we can help maintain that directional control going forward, right? This doesn't require any input from us. It works on its own, and it works independently. Okay. Now on the brake system, when we push the top of this brake pedal on the rudder pedal, that pushes a piston and pushes hydraulic fluid through a series of lines that gets routed all the way to the brake caliper. And when that fluid gets pushed there, it's going to compress those pads together around our disc. That's what's going to help us stop the plane or slow the airplane down. Any questions? All right. Next, we have our avionics system. Okay. Avionics are electrical systems used on the aircraft, which would include our electronic flight displays, such as our G1000s, G500s, or our GPS system, like the G430. Okay. You guys might have learned about this in our flight instruments lesson, learned a little bit about it, but our electronic flight displays can give us a moving map and GPS information, plus as well as airspeed, altitude, attitude, heading, vertical speed, and so on and so forth. All of that is incorporated into our avionics. Does anybody have any questions regarding the avionics system that you might have gotten answers to before, or something that you're not sure about? Thumbs up. All right. ADS-B is our automatic dependent surveillance broadcast system, right? Automatic because it automatically transmits information with no pilot or operator involvement required, right? Dependent because it's dependent on the position and velocity vectors that are derived from our global positioning system, our GPS. Surveillance because it provides three methods of determining three-dimensional position and identification of an aircraft. Three-dimensional would be latitude, longitude, and altitude. Then broadcast because it transmits the information available to anyone with the appropriate receiving equipment. So ATC has the appropriate receiving equipment, and if we can see traffic on our ADS-B in system, then we have the appropriate receiving equipment. ADS-B out is the only mandated requirement. ADS-B in, so basically information coming into our aircraft, is not required, but we are required to have ADS-B out to be broadcasted. Okay, that's required under the Mode C veil, so that's the 30 nautical mile veil that surrounds a Class Bravo. It's required in the Class Bravo, required for a Class Charlie. If we're within 12 nautical miles of the coastline, ADS-B is required, right? That is the continental US ADIS, so the aerial defense zone. But that's between 3,000 and 10,000 MSL that is required. Above 10,000 feet MSL in Class Echo, we are required to have ADS-B, but if it's within 2,500 feet above ground level, then it's not required. Okay? So if we have an airport on top of this mountain and we're 2,500 feet, AGL is not required. Then of course, in class alpha, it is also required again. Okay? Another thing to note here is while we require at any point we're in that mode C veil of class Bravo, we don't require it underneath the shelf of a class Charlie, but we do require it overflying. If we're flying above a class Charlie, it is required as well. Any questions about the ADS-B requirements for various airspace? All right, transponders. A transponder is a receiver and transmitter, and it's a simple means for an aircraft to communicate its position with air traffic control. So ADS-B out and transponders with altitude reporting mode turned on, that would fall under mode C or mode S transponders. Substantially increase the capability of surveillance systems to be able to see an aircraft. This is going to provide air traffic controllers as well as pilots of suitably equipped aircraft that have ADS-B in or traffic collision avoidance systems, increase situational awareness, and the ability to identify potential traffic conflicts. So this is where we would squawk one of these codes if we had an emergency, a radio failure, or if we were being hijacked. Okay? 1200 is our generic VFR code, or we can squawk a unique code that ATC wants us to squawk when we are on a IFR flight plan or getting VFR flight following. Right? Does anybody know how many different codes can be generated? Kyle?
Is it 4096?
4096. Yep. So we can have up to 4,096 different codes generated. That's why sometimes they'll call it a 4096 transponder. All right. Quick review of the pedostatic system, right? This is a pedostatic system of a steam gauge or a six-pack. But our electronic flight display still uses a pedostatic system, right? But that information is channeled through, whether it's a Cessna, we have a pedo tube and then a separate static port. Remember that separate static port is located along the side of the fuselage. On the Archer, we have a pedo mass where we have a static and a drain port. A ram air port and a drain port, and then the static port is on the back. Okay. That is going to feed information on an electronic flight display to the air data computer. And it's going to do calculations to measure our airspeed, our vertical speed, and our altitude. On traditional six-packs, we have a vacuum system that is going to power our gyroscopic instruments and our attitude and our heading indicator. Okay? It's engine-driven once again, spinning from the power of the engine in order to generate vacuum, pulling air through that filter, through the attitude and through the heading indicator, and simultaneously through a suction gauge. So that way we can know that the vacuum system is producing the correct amount of vacuum that we need for its operation. All right? If it's too much or too little, then our information that we're getting from the heading and the attitude indicator would not be reliable. So we have a vacuum relief valve, which relieves the pressure, and then any excess is exited overboard. So it's a vent line that pushes out any excess vacuum that is not needed. Okay. If you have an aircraft with a G1000, but it still has standby attitude and standby pedostatic instruments that are like this, then it will still have your vacuum system. Okay. If it uses a standby instruments, so extra set of instruments that uses another electronic display, then it might have a vacuum system. Right. Normal operating range of the vacuum system is between 4.5 and 5.5 inches of mercury. Questions, confusion? Anything needs to be clarified? All right. Environmental systems, right? This is just like your AC or your heat in your car. In our planes, we have cabin heat and fresh air vents. Cabin heat works by pulling air that flows over our exhaust manifold, because our exhaust manifold is releasing heat from the combustion that's happening in the engine, right? So it blows over the exhaust manifold, and then it's routed into the cabin to give us heat. Okay? When we're not using that, we could close it off, that heat is routed outside. The danger with this is that if there is a crack in the exhaust or there's exhaust gas leaking out, that can mix with the fresh air and put carbon monoxide into the cabin, right? So be wary when you're using cabin heat, not carb heat. If you're using cabin heat, you want to look at one of those stickers that ATP has in the aircraft. We have these stickers that will detect carbon monoxide, because carbon monoxide, we can't smell it. We won't detect it, until it starts possibly affecting us and we might pass out. So if you look at that card, it has like a little orange sponge circle. That orange sponge will turn black if it detects any carbon monoxide, right? You want to turn off that cabin heat, open up any windows, let fresh air in to clear it out, and then that card will turn back from black to orange. Okay. So it's not to scare you from using cabin heat. You can use it, but just understand that, the potential hazards of using it, and keep an eye out. Then we have de-icing and anti-icing equipment. All right. De-icing equipment simply removes any ice that has built up. Anti-icing is designed to prevent the formation of ice. So we spoke about carb heat before, right? If you spoke about carb heat, that is technically an anti-icing device. It prevents the formation of ice in the carburetor. Can it still remove ice if we suspect carb icing? Yes. Okay, but don't get it confused. It's still an anti-icing device. Another anti-icing device would be our pitot heat, right? On our pitot mast or our pitot tube, we can turn on pitot heat to prevent the formation of ice, which is the usual process. You want to turn it on if you're operating in temperatures below a certain temperature based on whatever your POH says, and you're flying in visible moisture. This typically doesn't become a problem for pedostatic icing unless you're flying in IMC, but it doesn't mean it can't happen. So pitot heat, carb heat, Those are anti-icing. De-icing would be any other type of equipment that can remove ice after it has formed. We are not certified to fly into known icing conditions, okay? We cannot fly into known icing conditions because we do not have the proper equipment, okay? Lauren,
Is that just an ATP requirement or is that like an overall private pilot requirement?
for being able to fly into known icing?
Mm-hmm.
No, yeah, that's a FAA thing. Your aircraft has to be certified to fly into known icing conditions. Okay, so you think about your more expensive aircraft, your jet aircraft, they are designed to fly into known icing conditions because they have equipment to combat that. We don't have enough equipment. Manuel,
What about ground icing conditions? Is ATP allowed to use icing and de-icing fluids?
yeah, some of the northern locations, they'll have that on hand where you can go and try to help spray the aircraft and get the ice melted off. Yeah. Any other questions? No? We're all good? Nicole, what you got for me?
It says resource linked in the Zoom chat. Are you gonna be linking a resource?
Let me just make sure. Oh yeah,
Thank you.
let me just thank you for reminding me. Always like to double check the links to make sure they're good, and there you go. So this is from aopa.org. It's about a 12-page write-up on icing, aircraft icing. Yep. All right. Cool. We've made it through the longest one. All right. I'll give you guys to top of the hour. All right. We have 2 more slides to go through. That leaves us about an hour and a half. That should be plenty of time. Okay. Oh, I am muted. All right. Let's talk about emergency operations. Get those cameras back on so I can know everybody's here. And all right, there we go. So what do we do when we have an emergency that we need to deal with, right? So it's a required task of the private ACS. It's not only important to know for your check ride, but you should know them for everyday flying as well. So we'll look at systems and equipment malfunctions, emergency descent, emergency approach and landing, and then the ABCDEs of every emergency. We'll also look at emergency equipment and survival gear. So all emergencies call for landing as soon as practicable, right? But some will also call for an immediate landing. Okay. The key to managing an emergency is being familiar and practice with the procedures that are found in your POH, in your pilot's operating handbook. So every aircraft is different. Every aircraft manufacturer is going to want you to handle any emergency procedures slightly different for whatever aircraft that it is that you're flying. That is always found in section 3 of the operating handbook. And it lists out all the different types of scenarios and what you're supposed to do in that scenario. So in systems and equipment failure, here's what we will cover. We'll look at a primary flight display failure, multi-function display, the attitude and heading reference system, the air data computer, pedostatic failures, flight controls, electrical, engine, fires, vacuum, or icing. Okay, so we need to determine what has failed and what action we will take for each failure. So we have the PFD and the MFD. All right. As we answered from the scenario, you use your standby instruments in this case. So if we have a PFD, MFD failure, we would use our standby instruments to give us the information that we're looking for. All right. When we lose the PFD, what do we lose that we don't have a backup for? Right. So if we lose our PFD and we don't necessarily have a backup for it, with our standby instruments, we only have airspeed, attitude, and altitude, right? We won't have VSI, we won't have rate of turn or slip skid indication, outside air temperature indication, or true airspeed, or all that extra information that the G1000 might give us. If we look at the G1000, right? We'll have this little red button here called a display backup or revisionary mode. So in this case, where we lose the PFD, let's say the PFD stopped working, but everything else is still working, we can push that button, and that'll put all of that information for our altitude, airspeed, attitude, heading, etc. on our MFD. So for an HSI or CDI, we would use the CDI page on the GPS. That will give us information that is relevant to our heading or our course deviation. In ATP, we use the MFD for situational awareness. Okay, we don't use the MFD as a direct guide, but we use it for situational awareness. If the MFD fails, we still can have a moving map in our engine instruments on our PFD. All right. All right. The AHRS, that is our attitude and heading reference system, right? If that fails, we then lose our artificial horizon and we will lose our heading, right? But we still can have a magnetic compass to tell us which cardinal direction we're going, right? We can also use our standby attitude indicator to replace our attitude indicator on our PFD if the AHRS fails. Okay. So the PFD has a compass rose like this. The PFD compass rose is still available, but it's now displaying your ground track. All right, it's not going to display your heading. It's going to use the GPS information to tell you which direction you're traveling over the ground, right? While our heading would tell us which direction nose is pointing, the ground track can tell us which way we're traveling over the ground. So it is possible, depending on the way which way the wind is blowing, that you're facing a little bit to the left, but you're traveling in a straight line, right? So our PFD is going to use the ground track information and tell us which direction we're traveling over the ground, not necessarily which way our nose is pointing. Any questions with the AHRS? Now we have our ADC. This is our air data computer. If that fails, that is going to, we're going to lose all the information regarding our information from our pedostatic system. So we would lose airspeed, altitude, and vertical speed, right? We have a standby altimeter and we have a standby airspeed indicator that we can use, but we might not have a standby VSI, a vertical speed indicator. The air data computer can no longer calculate our outside air temperature or our true airspeed, okay? But you will learn through experience that you do not necessarily need to know that information at all times, right? The main things that you would need is your altimeter, your airspeed, and your attitude. All right. Let's talk about the pedostatic system. Quick review. What instruments are affected if we have the static port is blocked?
Vertical speed indicator and altimeter.
Vertical speed indicator and altimeter. Who had raised their hand? Remember somebody? Hold on. Jeremiah.
Yeah, I was just gonna say that the altimeter and the vertical speed indicator goes when the static port goes.
Okay. What about the airspeed?
Airspeed only goes if the pedo tube goes.
All three of
Static
them.
port is connected to all three. Okay. So remember that the static port is connected to all three. So it's going, if this gets blocked, it's going to affect all three instruments. Okay. So with that being said, what instruments are affected by the pedal tube? The pedal tube has a blockage. Is it still all three of them?
Airspeed indicator.
Just the airspeed indicator. Okay. What can cause this type of blockage?
Icing could be a factor.
Icing, good. Right?
Debris, like bugs.
Debris, bugs, dirt. Yep. there's one more. It might be a little bit embarrassing if you go to take off and you realize your airspeed's not working.
You never took out the plug for the protection?
Right, the pitot cover, right? You forget to take that off. That happened to me in my private pilot stage. We went to do a P-flight, get already almost started the plane and looked out to the left and the pitot cover was still on. I was embarrassed just from that alone. Right? Good. So static port, it affects all three instruments. Pitot tube affects only the airspeed. So with the ram air hole, if that is clogged, but the drain hole is open, the airspeed will simply read 0. If the ram air is clogged and the drain hole is clogged, that pressure gets trapped inside the pitot system and the airspeed indicator will act as an altimeter. If we have a static port blockage, airspeed indicator reads correctly, but only at the same altitude only at the same altitude that that blockage occurred. Altimeter, it will freeze the indication on the altitude at which it was blocked. The FIA side will freeze on 0, okay? And then we would have to use an alternate static source, right? So if we have an alternate static source, that is gonna bring static, instead of looking for static pressure outside of the aircraft, we're gonna look for static pressure inside the aircraft. When we use the alternate static source, airspeed will read a little bit faster than it should. Altimeter will indicate a higher altitude than it should, and the vertical speed will momentarily show a climb until it equals back out in pressure and it'll read 0. All right? How are you guys feeling about the pitot static errors? All right, flight control failures. All right, we can have failures of our flaps, right? Less likely in the Archer, but more likely in the Cessna. Archer, remember, it uses the mechanical flaps. Archer uses an electronic motor. So if we go to put our flaps in and we can't deploy our flaps, then we aren't able to use flaps and we have to use a no flap approach and landing. All right, that is going to require more runway use. We're going to be coming in at a faster airspeed to land. All right, so we would need to use more runway. We might float longer down the runway. And it'll call for a slightly more nose-high approach, right? Because we have to keep the nose a little bit higher in order to maintain our airspeed coming down. If we just point the nose down and try to descend, then we would end up building up too much airspeed for a safe approach to land. You can also have an asymmetric flap deployment where one flap is extended further than the other. Okay, that can cause a roll to the side with no or uneven flap deflection or deployment. And then it could also cause yaw. So just like with the ailerons, right? Where we're creating more adverse yaw, if we have one flap deployed, but the other one's still up, we're gonna create more drag, we're gonna generate more lift on one side versus the other, and it's not gonna be even. We would have to counter that. We're going to counter that rolling tendency with the aileron. We're going to counter that yaw tendency with the opposite rudder to help keep the plane coordinated. All right. Help keep it from being in a cross-control condition. That is when you have the plane flying in one direction, but you have the rudder or aileron input in the opposite direction. That can easily lead to a stall at low airspeeds. If you're going to try to land with an asymmetric flap deployment, you try to land with a crosswind from the side of the, you do not want to land with the crosswind from the side with the extended flap. So if the flap is down on the right side, it's down on this side, you don't want the wind blowing from this side. Okay? Because in order for us to fly a crosswind landing, we want to be able to put the ailerons into the wind, whichever the way the wind is coming from. If the wind's coming from this way, the plane's going to want to roll to the left. So it's better if we could land with the crosswind coming from the left. You'll learn more about that when you guys practice crosswind landings. Then we have a loss of elevator control, right? Elevator control the elevator is controlled by two cables. We have a down cable and an up cable. And when that cable breaks, forward yoke input is not registered if the down cable breaks. So you can still move the yoke forward, but it won't do anything to the elevator. And vice versa. If the up cable breaks, when you pull back on the yoke, you can pull back, but it won't do anything on the elevator. All right? To counter a loss of control, you would have to use your trim wheel, right? So if we want nose up, we got to use a lot of nose up trim. If we want nose down, we got to use a lot of nose down trim. Okay? Any questions with loss of flight controls? You sure? 100%? Yeah. If we have a alternator failure, then we're not going to be generating electricity anymore to power our electronics. It's going to resort to using a battery, but only for a limited time. We can expect to see a low voltage annunciator or any annunciator lights illuminate. The ammeter will read 0 on the Archer, and then we'll have a negative reading on the ammeter for the Cessna. Always with an emergency, we want to run the checklist first, right? Because if there's something that we can do to get it working again, that's better than not having it working, right? But if we run through our checklist and we realize that we cannot get it back, we need to reduce the electrical load to a minimum. So turn off any unnecessary electronics that we don't need and land as soon as it's practicable. All right. On the G500 Archers, in the event of an electrical failure, the standby attitude indicator will continue running for 1 minute on its backup battery. But in order for it to continue to run on its backup battery, you must press the standby power button on the instrument panel. Okay. We have the engine power plant malfunctions, all right? We got to analyze and think about possible causes. So always remember the 3 components that we need for the engine to run. What are they?
Air, fuel, spark.
Air, fuel, and spark, right? So if we have a carbureted engine, we can check for carb heat. If we have our fuel selector, make sure our fuel selector is set to the right tank. Make sure that our fuel shutoff valve is not triggered. Make sure that put our mixture all the way forward, right? Try to get fuel back in there. Try to get power out the engine. Check your magnetos. Make sure that magnetos are on. Check anything that's going to control fuel, air, or spark. And we could run 2 different checklists. We have an engine power loss in flight or a power off landing. So if we run our engine power loss in flight checklist and we can't get the engine back running, you know, we check our fuel, we turn on our auxiliary electronic fuel pump, and we can't get the engine back running, then we need to run the power off landing checklist. That is going to help us prepare to do a landing with no engine power. Okay. And where can we find checklists for this information? In the POH, yep. In the POH. Okay. On the vacuum system, remember it operates our gyroscopic instruments, the attitude, the heading indicator, and the turn coordinator, right? What's different about our turn coordinators that we use now? How are they powered? So do our turn coordinators that we use now use vacuum? Anyone? Am I losing you guys? No? Yes? Kyle?
Is it the engine that would power it?
Not necessarily, but what it is that they used to use a vacuum system to power your turn coordinator, your attitude, and your heading indicator. More recently, in the traditional 6-pack, they started using electronic turn coordinators. So it uses electricity to spin, a motor spins the gyro inside the turn coordinator. Right? So it used to be vacuum driven, now most of them are electrically driven. Okay? But it doesn't mean that you could not one day be flying something that has an old style turn coordinator, which uses a vacuum pressure. Vacuum failure on conventional Cessnas with a 6-pack, you'll see an annunciator panel light. A light will come up saying that there's low vacuum pressure. On the G1000 Cessnas, on the standby, you'll see a flag pop out letting you know that the vacuum pressure is low, and an annunciation on your primary flight display. Okay. Most times though, we do have 2 vacuum pumps as a backup and redundancy. Much like how we have 2 magnetos and 2 sets of spark plug on each cylinder. We have 3 types of icing: structural, induction, and instrument. Induction icing is anything where the airflow is being brought into the engine, so like our carburetor or our intake, right? We can get icing there. Structural icing is any ice that can form on the structure of the aircraft, and that could be clear ice, which is like a thin sheet of ice that freezes over the airfoil, and it's hard to detect. Rime ice looks more opaque like this in their color, and then mixed is a combination of both. Okay. Instrument icing, we kind of spoke about already. We could get pedostatic icing on our pedostatic instruments. Right? Then we also have frost. Frost is the ice crystals that are caused by sublimation. And when both the temperature and the dew point are below freezing, frost, just like icing, it disrupts the airflow over the wings as well as drastically reduces the production of lift, while also increasing drag. So all things that we do not want to do. We do not want to decrease lift, and we do not want to increase drag. Okay. Questions? All right. So how do we handle an engine failure? It largely depends on the altitude that we are at. You have to ask yourself, do we have enough altitude in order to run a checklist, right? So if your engine fails after takeoff at 100 feet, what would you do?
Would you pitch for your best glide speed?
Pitch for your best glide speed. It depends on where you are. If you have enough runway in front of you to land, you're only 100 feet, just land on the remaining runway, right? If not, pitch for best glide speed and find somewhere to put it down, typically straight ahead in front of you. Don't try to turn. Okay, if you try to turn, you're gonna lose altitude quicker. All right, what about 500 feet? That is when you're gonna really have to pitch for your best glide speed and find somewhere to put the plane back down. Right, but then we have 1,000 feet. So it all depends on what type of time that at the time that a failure occurs is giving you. Right, even at 1,000 feet, you don't have much time to try to figure out what's going on or try to run a checklist, right? Versus if we were at 6,000 or 7,000 feet, we have time, right? We can pitch for best glide, find the best place to land, and run through our checklist, which we're going to go through in a second. But the POH has checklists depending on when the failure occurs. And then before every flight, you're going to do a pre-takeoff brief. That is going to have you verbalize what you would do in the event of some type of engine failure or an abnormality during the takeoff roll, or with enough runway to stop, or immediately after takeoff. Okay? Another maneuver that you guys are going to practice and you have to display on your check ride is an emergency descent, right? So the purpose of an emergency descent is to lose altitude as fast as possible, all right? While we're not going to be flying high enough for it to worry about a loss of cabin pressure, we could also be dealing with scenarios like an engine fire, or if we have a really sick passenger and we need to get down to land as soon as possible, right? But you want to stay within structural limits of the airplane. So you want to descend as fast as possible without destroying or damaging the aircraft. We can also alleviate that by using bank. If we turn the plane 30 to 45 degrees of bank, that will maintain a what we call a positive G load or positive load factor on the airplane. Right? That's going to keep us from having negative G's on the aircraft and potentially causing damage. So let's walk through some steps. We have 3 types of emergency landings: forced landing, precautionary, and a ditching. Forced landing is when you have no other choice and you need to put that aircraft down, such as a complete engine failure. Precautionary landing is you suspect something is wrong with the engine, but it's still running for now. So I'm going to land as a precaution before something bad happens, right? Or something gets worse. Then you have a ditching. A ditching is a forced or precautionary landing on water. Okay. You got to do your best to keep the cabin intact, all right? Or relatively intact as much as possible. You have to consider your landing field. If there's anything that could possibly run into, trees, bushes, things of that sort. The wings, landing gear, the fuselage will absorb the violence of stopping procedures. All right. So if you try to land and you land it real hard, then you can damage the aircraft. You want to try to land that aircraft as soft as possible in that scenario. All right. That will avoid any forceful bodily contact with anything in the interior, such as a dashboard and whatnot. So we want to configure for landing. That is establishing our best glide speed. We want to consider the wind direction, because like I said, whenever we take off and land, we want to land with the headwind, right? We want that wind blowing straight on us. Same thing in emergency landing. If you have time and you can put that plane into a headwind, figure out which way the wind is coming from, and land that plane into a headwind, that's going to help you stop and help you get down. Use flaps, right? What flap setting is appropriate for the type of landing that you have to do? Whether it's going to be a soft field or a short field landing. So if you're landing on a grass field, a dirt field, right? Anything other than hard surface. And then if you can, enter the normal traffic pattern at traffic pattern altitude. That's what TPA, right? So you practice these things when you go for your training. You practice emergency approach and landings, and you have to do whatever it is that you need to do to land safely. Okay? Common errors that we see is a failure to use the most suitable landing area, right? You don't want to be in a panic and look over to your right and see like a beach or a field that you can land in, but you forget to look to your left and you see an airport to your left, right? Which would be better? Field, beach, or the airport, right? Failure to fly the most suitable landing pattern for existing conditions. So we want to consider the winds. We want to consider what that's going to do to our aircraft. If we're flying and we have a massive headwind hitting us in this direction, you know, we might not be able to glide as far. We might have to turn back the other way and use a tailwind to help get us to someplace that is within our reach. Failure to use checklists. Like I said, time permitting, you always use a checklist. You might have everything memorized in your head, but you might forget something in that moment under panic. Okay. Then also improper airspeed control. The longer you can hold your best glide speed, the further you can go. Right? So if you have established yourself on your best glide speed and you're able to hold that, you will have a better chance of reaching and gliding further to your distance. Okay. Questions? All right, here we have this the mnemonic for A, B, C, D, E, just like the alphabet, right? This is your A, B, C, D, E's of every emergency. All right, pitch for best glide speed. Hold your best glide speed, use a trim wheel to reduce your workload. So now you're not worried about your glide speed as much. B is for find the best place to land, right? Immediately try to find an airport or other landing spot within gliding distance and turn toward that spot. Consider the factors associated with landing on roads, fields, water, trees, etc. You can review chapter 18 of the Airplane Flying Handbook for more information on some of those hazards. But just to name a few, you might have power lines, you might have cars, right? Overpasses on the highways, things like that. You can use the nearest page on your GPS. The nearest page knows, your GPS knows where you are and can tell you where the closest airport is. ForeFlight has a glide advisor, which will build a ring around your aircraft on ForeFlight, and that can show you how far you are able to glide. And if not, there's rule of thumb, right? And this is not in all scenarios, but the rule of thumb is every 1,000 feet of altitude that you lose, you can glide about 1.5 miles. Okay? So if you have 2,000 feet of altitude to give up, then that's about 3 miles. And I always say about 3 miles because you have to consider what the winds are doing to you as well. In one direction, it might give you 2.5. The other direction, it might give you 3.5. Because the wind is blowing you, is either blowing you backwards or blowing you towards the spot you're trying to go. Time permitting, you have enough altitude, run your checklist. All right, because what's better, an engine that stopped working or an engine that we can get back working again? Right? So if we can get that engine running again, we at least have a few extra minutes for us to do a precautionary landing as opposed to a no engine landing. D is for declare an emergency, so let ATC or somebody know what's going on, squawk 7700. Put the frequency on guard frequency 121.5. Talk to somebody, let them know what's going on. And activate your ELT, that's your emergency locating transmitter. Okay? Lock your seatbelt, make sure that your seatbelt's fastened, unlatch the doors, right? Because if you end up hitting something, you don't want the doors to get crushed in to where you can't get out. And then review any egress procedures. So which way are we going to exit the aircraft once we've completed this emergency landing? If the engine propeller happens to be to still be rotating forward, we don't want to run towards the front of the aircraft, right? So we run to the back. We run, get out, and exit towards the back of the aircraft. So those are all things, that is your ABCDE checklist. But the most important thing, fly the airplane first. Okay? Aviate, navigate, then communicate. Fly it first. All right? Considerations for finding your best landing area. How far can you travel? Right? Like I said, consider the wind. If time permits, you could use your resources, the nearest airport page on your GPS. But as soon as you find your best place to land, you want to turn towards that spot immediately. Okay? You don't want to keep giving up altitude before you start heading towards it. Right? And choose a landing area wisely. Right? Highways. The pros of having highways is that it's large, right? The con would be that there's lots of traffic. There's power lines, bridges, like I said. Roads might not have as much traffic, but they're also very narrow, right? Too many power lines. Water, there's still a chance of survival, but the con is that if the plane is underneath the water, pressure might make it hard to get out the aircraft to open the door, right? And you also need to know how to swim. So always think about your plan of action. My private pilot instructor taught me to, as I'm flying along, even though everything's going fine, every once in a while, just look out the aircraft and just think to yourself, all right, if things were to go bad right now, where can I put this aircraft down? Right? Where can I land it? That is going to eliminate you having to think about it after the emergency occurs. Okay? Checklist, checklist, and checklist, right? They're going to help you try to troubleshoot the problem and fix it. They're also helpful because you might not always be mentally sound in an environment like that in the midst of an emergency in order to catch everything. That one thing that you miss on that checklist in your head might be the one thing that helps troubleshoot the aircraft, right? So ask yourself, what kind of emergency is this? So we're going to discuss that. You're going to discuss with your instructor the different types of emergencies, whether your engine is running rough, whether you have an alternator failure, complete engine loss, sick passenger, engine fire, wing fire, something, right? So I encourage you guys to look over the different emergency checklists and become familiar with them. Make your emergency known to the public. Let them know what's going on. Squawk code 7776 7500. Mayday, mayday, mayday on 121.5. If you're not already talking to ATC, whether that's tower or a flight service station or air route traffic control center, let somebody know what's going on. Okay. If you hold the comm button on your radio panel, if you hold it down, that'll automatically switch it over to 121.5. So that way you're not fumbling with the knob. You hold that COM button down and it will switch it to 121.5 so you can broadcast your Mayday calls. And then we have ELT and egress procedures again, right? ELTs have to go through 12 calendar month inspection, or the battery must be replaced after 1 cumulative hour of use, or when 50% of the useful life has expired, okay? They will automatically trigger on impact when they're impacted, but you can activate them manually. There's going to be a switch in the cockpit where you can turn on the ELT. That's going to broadcast a signal over the radio waves, and it's going to broadcast a signal that ATC and emergency service can use to find you. Okay? In the event that you can't stay near the aircraft, you can always try to grab that ELT and bring it with you, right? It'll have its own battery power. You can carry it with you, so that way if you have to move away from where you put the plane down, emergency services could come to your location and not the plane's location. All right. 2 acronyms that you can use to brief your passengers is the SAFE acronym. So that's for seatbelts, show them how to use the air vents, where the fire extinguisher is located, and any other type of survival equipment that you might have. Now, when it comes to the fire extinguisher, we use the PASS acronym. Pull the pin, aim at the base of the fire, squeeze, and then sweep. All right? Also brief them on the ELT. What's the purpose of it? And in case we need to grab it. But just know ATP aircraft only has an ELT and a fire extinguisher. All right? It does not have any other survival gear or equipment. Okay? That's why ATP doesn't allow us to fly over water outside of glide distance of land. So if you are flying over a body of water, you got to make sure that if you to lose your engine, you can glide back to land. All right, so if we have an emergency, what code are we going to squawk?
7700.
7700, 7700. Good. All right. What does the A in ABCDE checklist mean?
Airspeed.
Right. So your
Airspeed.
best glide speed. What about the B?
Best landing location.
Best place to land. All right. C.
Checklist.
Checklist. Right. Time permitting, use your checklist. D.
Declare for emergency. Declare emergency.
Exactly. What's the frequency that we could declare emergency on?
7700.
121.5.
121.5.
121.5. Good. E.
ELT, emergency landing.
ELT and emergency landing, emergency procedures, landing procedures. Good. All right, any questions?
I do have a question.
Yeah.
Will we do simulated engine failures like leading up to, say, a known airport? Is that something that we'll do?
Yeah. Like going to, if you're flying near an airport.
Yeah.
Yeah, your instructor might intentionally do it, not tell you, but intentionally do it near an airport just to see if you're being aware of your surroundings. You have that situational awareness to know that, okay, there's an airport right below me or right up to my side. I'm just gonna go ahead and land there, right?
Okay.
Now, you're most likely not going to do it in a scenario where you simulate that you're losing it at an altitude and all the way down to actually land on that runway. but you would simulate it down to a certain altitude, and then you would go ahead and just recover. Once they see that, okay, you're able to glide to make the airport, and you thought about the wind direction, how you're gonna enter, you're talking through it, you set yourself up correctly.
Okay, cool.
But yeah, it won't necessarily be like from altitude all the way down to the ground. No. Yep. Any other questions? All right. Let's take 5, and then we will come back and finish up the last slide about VORs. Okay. All right, guys. Let's go ahead and talk some more about VORs and some advanced navigation techniques or equipment. All right, before we keep going, any questions regarding anything else we covered before? All right. I'm gonna keep asking, just to make sure. So once again, this is part of your private pilot ACS, navigation system and radar services. We have to demonstrate that we have an understanding of ground-based navigation, satellite navigation, radar assistance to VFR aircraft, and transponders. Read references that you can use: Risk Management Handbook, Instrument Flying Handbook, Advanced Avionics Handbook, the PHAK or the Pilot's Handbook of Aeronautical Knowledge, and the AIM. So we have two types of navigation systems: ground-based and satellite-based, right? Ground-based would be VOR, NDBs, or DME, which is distance measuring equipment. And then satellite-based, which is GPS. All right. What does VOR stand for? Anybody remember? Manuel.
Very high frequency omnidirectional range.
Very high frequency omnidirectional range, right? Seems like a pretty long name for just a short acronym. But yes, that's exactly what it is. All right. So what a VOR looks like, or a type of VOR. But we have three types. We have a VOR, which is standard. That is just going to give us 360 degrees of directional navigation. Right? Then we have a VORTAC. This is a VOR equipped with military tactical air navigation. For short, they call it a TACAN, right? And then even shorter, they call it VORTAC. So VOR with TACAN, or tactical air navigation, is a VORTAC. Then we also have VOR with DME. That's a VOR with distance measuring equipment. Okay. So VORs are still commonly used navigational aids in civil aviation. Right? They are oriented to magnetic north and then provide the 360 degrees of navigation to or from the station. We have different ranges for the VOR or VOR DME, and they will provide either a to or from direction. So a to is us flying to the VOR. From is flying away from the VOR. Okay. Both VOR and DME and both VORTAC provide the azimuth, so the 360 degree information from the VOR in order to receive those omnidirectional radios, as well as distance information from the station to the aircraft. So basically, distance from your aircraft to the VOR. A regular VOR does not provide any distance information, right? Before we had GPS, VOR was considered state of the art. Now it's getting kind of outdated, right? But with GPS technology, we are advancing and we have a lot more accurate methods of navigation. right? But these are still accurate and can be useful to us. So the station sends out signals called radios. And each radio is a specific course either to or from the station. So we have, let's say we have a station here in the middle, and we have magnetic north. This would be the 360 radio of that VOR. This would be the 180 radio of that VOR. And so on and so forth, all the way around. Now, all 360 are shown here because, 021, 025, it's not numerically shown, but we can be on a 315 radio or a 135 radio. Everybody get that portion of it? Now, just like runways, right? We can have a 09 runway and a 27 runway. So we know that 27, this is facing in the west direction, this one is facing in the east direction. Same thing on the VOR. We can be tuned into the 270 radial of the VOR or the 090 radial of the VOR. So if we look at it, what it looks like in a traditional cockpit, what radio is this VOR tuned to? How would you guys read this?
Um, 255.
Yep, because we have 240 here, 245, 250, 255. So here we would be on a 255 radio of the station. Okay. The flag here is showing us whether we are to or from. In this case, we are from the station. So in this, Sam, what's up?
Why would it read to or from? What's the meaning there? I don't understand.
That's what I'm going to show you on the next slide now,
Oh.
right? It's okay. So this is our VOR, okay? Right? This would be our 255 radial here, this line. All right? Our aircraft is located on the same side that the radio radiates from. So this would be giving us a from indication. If we were tuned into the reciprocal, so let's say we had on the opposite side of the VOR, a radio being coming out. So, sorry, 255. The opposite of that would be what? 075. Okay, you see that? So 255, 075. If our aircraft is located here and we have 255 dialed in on our indicator, then that would give us a from indication. When we go to the opposite side of the VOR, we have the reciprocal, right? Or 180 degrees from that. This would be a 075. That would give us a to indication. Go ahead with your question, Sam.
So the indication is just in relation to positioning in regards to the VOR?
Yes.
Okay.
And what radio you're dialed into.
Right.
Right? Because we could be, this is the same line extended through the VOR, but because this one is on the other side of our position, this would give us a to indication.
What would it read if you were on like a 90-degree angle oriented with the dialed into like a 90-degree VOR to it? No.
You mean like that?
Yep, that's the one.
Guess what? It's still going to read It's still gonna read from.
Okay,
The position, the orientation which your aircraft is facing, it doesn't matter. It could be facing this way, it could be facing this way, or it could be facing that way. You're still on that same radio. Imagine if we were a helicopter just hovering in that same spot. Right, but we just rotating in circles. It's still gonna say we're on a 255 radio with a from indication. Okay,
gotcha.
so
Oh,
if
so
we're
it's only in regard to the orientation of the degrees to which you're dialed in, not the degree that the airplane is facing. Doesn't matter.
yes,
Okay.
yes, exactly. It does not matter which way you're oriented. So if we know that we want to fly away from this VOR and we're facing in that direction, we want the from indication, right? But if we want to fly to the VOR, we want a 2 indication, but we're not gonna get a 2 indication tuned into 255. We have to tune into the other side, which in this case would be the 075. Easiest way to determine the opposite is to look at it on the opposite or to subtract 180 degrees, right? Because we know if we do a 180, that reverses on the other side. So if we want a 2 indication, we would dial into the 075 and that'll give us a 2 indication. If we want to fly away from it, we need to dial to the 255 and fly away from the VOR. But it doesn't matter which way the plane is facing. If we're on this line, then we are going to, it's going to show that we are lined up with that radial. Any other questions? Anybody need that again?
So would you have to just manually dial it to the 075 if you wanted a 2 heading?
Yep.
And then so is that literally just like from 0 to 180 gives you a 2 and the opposite gives you a from?
Say that again, you kind of broke up.
Like, so would like heading 1 to 179, 180 give you a 2 while the rest gave you a from? Like I'm not understanding why the 255 is a from and why the 075 is a 2. When you could fly in either direction on that same radio.
Right, it's relative to your actual positioning to the VOR and which side that line, that imaginary line is coming from, which way that signal is radiating from. Does that help you or no? It's okay, say no. I'll find another way
Not
to
really,
explain.
no.
Okay. So we have this line coming out from the VOR. Our aircraft is located on this same side. Okay?
Yep.
When our aircraft is on the same side that the signal is radiating from, that is going to give us a from indication.
Okay, I got it.
Okay? To have the
Yep, it clicked. I got
indication, right, the plane has to be on the opposite side of the radio that we're dialed into.
Right. Got it. Thank you.
Yep, Kyle.
Yeah, that actually answered my question. Thank you.
Okay. Good. Any other questions? All right. So for the best result, we have to use it in combination with the heading or directional gyro, the heading indicator. You can even use your compass, but you need to know which way your plane is facing versus which way that line is radiating. Because now the plane is facing north and we're facing north, but we know that the radial that we are tuned into is something like that. All right, so that's going to give us that. This is not exactly lined up. to be honest with you, because that 255 should be. Well, no, that is. Don't get confused between this compass rose and the one on the VOR. All right. Think about it like this. In this example, to fly to the VOR, you need to dial in 075 to fly away from the VOR, fly the 275. Yeah, or the 255. But yes. So let's look at this example here, right? We're looking at we're dialed into the 360 radio of this VOR right here, of the Corona VOR. So that would be lined up like this. Okay? Now, this is our course deviation. Okay? This is our aircraft position. We also have a from indication. So if we know that we're tuned into the 360, where should we expect our airplane to be? On this side of the VOR or this side of the VOR? Manuel. You're still muted.
We should be located east of the VOR. Basically by your right. So the radial should be on the left.
Right, but just based on this from indication,
Oh, within
are we on the north or south side of it?
We should be on the north side of it.
Right, we should be somewhere over here on the north side, right?
Mhm.
Because where our aircraft should be, with the from indication, our aircraft should be on the same side that the radio is radiating from. Okay?
Yeah.
Cool.
Question.
Yeah.
Doesn't those deviation marks have like a
measurement?
Nautical mile measurement, yeah.
Yeah. It depends on which phase of your flight, but it's about each dot is 2 degrees. If you're there about 2 degrees off per dot. Right, so this would be 2, 4, 6, 7 degrees or so off. A full deflection would be about 10 nautical miles. So 2, 4, 6, 8, 10. So 2, 4, 6, about 7 nautical miles.
Okay.
All right, so we established that with the from, we have to be somewhere on this north side. This is our line that matches up with this line. And this is our aircraft. So for us to line up with this radio, which way would we need to fly? Charles, what do you think?
Sorry, can you repeat that? I'm still
So if this circle right here is our aircraft, right? On this indication, this is our aircraft and this is the course that we want to line up with.
Okay.
Which way would we want to fly in order to line up with this course?
Northeast.
Yeah, northeast. Wait. You're saying this way?
I don't see where you're pointing. Yeah.
No.
Just to get onto the line.
Yeah. So if we're here, we want to go to the left. Okay. Because remember, we said our aircraft is somewhere over here, but if our course is now to our left side, and this is us in the airplane, and we're looking at the course out the window to the left, that means that our aircraft would be located somewhere over here. Do you see that?
Okay, yeah. Yeah, I'm still focusing on like the rotational. Yeah, I get it.
Yeah. So don't focus on the rotational thing of it. I understand what you're saying.
Right.
It's a little off-putting, but from indication, we want to be on the same side as that radial. We have to be on the same side as that radial. And now this line is going to move left or right, depending on where the course is in relation to us. So if this circle in the middle is us, imagine if you look out your left window and you see that course to your left, right?
Got
We
it.
turn left to
Yep.
go towards. All right, Charles, you got that. Did I confuse anybody else? Just want to make sure. Okay. Cool. But remember, no matter which way we point our aircraft, it's not going to change that indication because it's not dependent on where we point. It's just depending on our position in relation to the VOR. Okay. You can also use cross radials. You can use two VORs to establish your position. So if we tune into one VOR and find that we are on that 140 radial, we can tune into another one down here and find out we are on the 050 radial, and where those two beams, if we was to draw a line on the 140 down this way and a line on the 050 going this way, that will tell us our positioning. Okay, we can see on the map that we're somewhere over here where those two lines intersect. Just to kind of reinforce that, let's draw a line from this other VOR. Actually, that's not another VOR. Let's imagine there was a VOR here, right? We just drew a line straight from this VOR, like that. Where the two lines intersect, that would be our position. Okay? So you can use two VORs to determine our approximate location. Questions? All right. Now here we have VOR in the glass cockpit. We use a combination of our heading indicator and our VOR/ILS display. Just like in the the 6-pack, except that this gives us a combination of our heading and our deviation needle. Right? So if we look and we're trying to fly to this course, where is this course in relation to our aircraft? Is it to the right or to the left?
The right.
To the right. So if we were to fly due east, we can re-intercept that. Okay? Even if we were to fly, let's say 060 heading, eventually we'll still re-intercept it, right? No matter if this line was extended like that. The glass cockpit will also have an OBS, or blue arrow feature, that will function like an automatic distance finder. And it will always just point in the direction of the pre-programmed VOR or waypoint or airport. All right. That's something that you guys can practice with your instructors when you actually get into it, if you have a glass cockpit, just to get a better understanding. But as opposed to being tuned onto a radio, the ADF works by, no matter which way you fly, it's always going to point in a direction that you need to go to get to that point. Okay, and that's what the OBS would do. It would be a button right here that you would push, and it's tuned to a certain fix or waypoint or a VOR, and it'll tell you how to fly, which direction you need to fly to get to it. VOR identification, right? We need a way to make sure that we're using the correct VOR. So we do that using a Morse code identifier, and each VOR has a Morse code that we can listen to. So we would tune into the VOR on this frequency and tune into our our navigation frequency, and listen for this Morse code. You just have to match up the beeps and boops to what you hear as to what you see on your sectional. All this is spelling out is the 3-letter identifier. So Goodland VOR is GLD, and that's all that is spelling out, but you don't need to know that. You don't need to know how to speak Morse code per se. You just need to be able to match this with what you hear. And that will tune in, you would tune into and ID the VOR, right? Once you hear that, you know that you're using the correct nav aid that you want to use. Right? Every 30 days, we have to check our VOR equipment. Okay? We can do that 2 types of ways, in the air or underground. Any check that we do in the air is going to require a tolerance or an allowable error difference of plus or minus 6 degrees, right? So if we were to tune into the 090 radio and it's off by 096, we are within tolerance. If it's off by 097, then it's not within tolerance. That's if you're doing it while you're in the air. You can do it in the air over a known landmark, along an airway. An airway is basically like an artificial highway that connects 2 different VORs. Or you can use a dual check where you have 2 different VOR antennas, and you can check both of them to see how close the reading is. We can do a check on the ground at a VOT, which is a VOR test facility. Not all airports have them, but some of them do. You would have to look at the chart supplement for that airport to see if it has a VOT. Then we have a bench test. A bench test is simply that where a mechanic will take the VOR equipment out of the aircraft, put it on their workbench, and test it. And then the ground check is the same type of dual VOR check. You can do that on the ground and check the error between 2 different, on the same signal, but 2 different VOR equipment. Sam?
Does the ground check allow for that 6-degree variation, or should there be no variation on the ground?
No, I was just about to get to that. The ground check is a little bit more strict. It's plus or minus 4 instead of 6. Okay? When it comes to interpreting a radial, radials go out from the station. So they go out, and bearings go in to a station, okay? So in this case, this aircraft, if it's tuned into the 360, then it'll be on a 360 bearing because it's bringing us into the station, right? As opposed to this one, it'll be on the 360 radial because it's going out from the station, this aircraft, okay? Try not to get too caught up on bearings and radials. As you practice it, the terminology is gonna come more into play. Okay?
When do you use a bearing versus a radial?
It just depends on if it's going towards the station or out from it.
Okay.
Some people end up using it interchangeably. Some people always just say radials. Some people, will just say bearings or radials.
Got it. So it just depends on if you want to navigate going like to the station or like with the
Right.
radials preference.
Yep.
Okay.
So these would be a bearing. This would be a radial. Manuel,
Just a quick recap. You use the OBS selector to choose the radial, am I right?
yes.
Okay.
So we have a way of calculating our what heading we want to fly to intercept a radial. Okay. So first we would have to find the difference between the current radial that we're on and the desired radial. So if we are on the 215 radial here and we want to get to the 250. So let's find the difference. 250 minus 215, that gives us 35 degrees. We then times that 35 by 2. When we times it by 2, we want the value to be no less than 20 degrees and no greater than 90 degrees. So when we do 35 times 2, that gives us 70. We then add that 70 to our current radial that we are on. That gives us a value of 285. So we will point our aircraft at a heading of 285. And that'll bring us to intercept at 250. And then we would turn to follow that radial. So find the difference, times it by 2. If you times it by 2, it has to be between 20 and 90, and then add that to the current radial that you are on. The easiest way to find whatever radial that you are on is to tune into the VOR and just twist that OBS, right? Keep changing it all the way around till that needle gets centered. Once that needle is centered, then you look at what value you're on. Then you'll see, okay, I'm on 215. I want to go to 250. 35 degrees, times that by 2, 70, add that to 215. Questions? We have some limitations when it comes to the VOR. One of the biggest ones is the cone of confusion. So think of it as like an inverted cone over the top of the station. As we fly along and we enter that cone of confusion, the signals become erratic. The CDI needle oscillates. The to from flag might disappear because it's too close to the signals from the radios in order to determine just one of them. Okay. After we fly over the station and we get back on the other side now, over here, our information pops back up and we'll see that to switch to a from flag or vice versa. And that's how we know when we have station passage. That's how we know that we cross over that VOR. Okay. So once it starts acting all crazy, and then it, gets all the information back and starts reading correctly again, that's how we know that we've passed over the station. VORs do have some limitations. Line of sight is one of them, meaning that you have to have no interference, nothing in between the aircraft and the VOR. So let's say, there we go. So let's say we had a wall right here. Okay. This aircraft can't reach this VOR, but it can reach this one. This aircraft can reach this VOR, but it can't reach that one. This aircraft, because it's at a higher altitude, it has a line of sight to both. Okay? So it cannot have anything interfering. Think of it also like a mountain, right? If there's a mountain between you and the VOR, you might not be able to pick up a signal. Another limitation would be misinterpretation. That is when you can possibly receive two signals on the same frequency. Reverse sensing. Reverse sensing is when you're trying to fly to a station, right? But you have a from flag. So remember when I said about the needle being to our left and our airplane being in the center of that dial? If we have reverse sensing and we try to fly to the left in order to center that needle, it's just going to get further and further away from us. We have to switch to the opposite, dial into the opposite of it, and that will stop the reverse sensing. Or we have to understand that for us to intercept it, we have to fly to the right, but that's going to bring that needle. It's going to pull the needle to the center. Under normal sensing, we fly towards the needle. If we're reverse sensing, we have to pull that needle to the center. Undergoing maintenance, that just means that when you go to listen to that Morse code identifier, you will not hear it. If you do not hear it, that means the VOR is undergoing maintenance or it's simply not working. So if we don't hear the Morse code, we can't use it. And then we also have limitations. Different types of VORs have different service volumes. Terminal, low, and then high. High VORs are going to give you the farthest signal that you can reach, up to 60,000 feet, and as wide as 130 nautical miles, between 18,000 and 45,000. Low would be between 1,000 and 18,000, and then terminal will be 1,000 to 12,000. They all start about 1,000 feet above the ground and work their way up. So those would be the service volumes. That's basically, if you're flying over here above 18,000, you won't be able to pick up a low or a terminal VOR, but you can pick up a high service volume VOR. Another thing we have to consider is other aircraft. We have to be careful because there could be a lot of general aviation traffic around VORs, right? You could be using it for practice, for training, right? Using it for navigation. Those are all things that we have to consider, right? Non-directional beacons. These are still state of the art in Africa, apparently, but we really don't use them out here as much anymore. In fact, they don't even test for them unless your aircraft happens to be equipped with an NDB system. But it uses a low to medium frequency band and is not affected by line of sight, but it is susceptible to electrical disturbances such as lighting. Okay. DME, that's distance measuring equipment, uses ultra high frequency it's automatically paired with a VHF station like a VOR localizer to give us distance information, and it measures in slant range. So instead of measuring, you know, two objects on the ground like an aircraft and a VOR straight line distance on the ground, it's going to measure the distance from where your aircraft is to slant range distance. So that distance from here on a diagonal. That's what slant range distance is. And it'll give you the direct distance from the aircraft to that station. Think of a VOR once again. And that includes altitude. So if you're passing directly over a station at 6,000 feet, that will equal to about 1 nautical mile of distance. Okay. We don't have DME and ATP aircraft because we have GPS systems, and GPS systems allow us to replace DME where it's needed. Right? So GPS system uses a satellite constellation that provides position, navigation, and timing services to us. In the US, we have GPS. Other countries have their own sort of satellite system. But GPS is what we use, and the same GPS we use in our phones, cars, airplanes, they're all the same. They all use the same satellites. But if we are going to use GPS for navigation, we have to make sure that we keep the database up to date, okay? Every 28 days, the navigation database will expire and a new one will come out. So if you're going to use GPS to navigate, we have to keep it up to date. That's going to update all of our GPS waypoints, airport locations, things like that, any changes that they need to make every 28 days. Then last but not least, we have our different types of transponders, right? Transponder equipment, if we have a mode A transponder, that is only to give us a code, one of those 4 codes, right? A 4-digit code, I should say. If we have a mode C transponder, that's going to broadcast a code, and that's going to allow ATC to see the aircraft's altitude. When we get to a mode S transponder, it's going to give a code, it's going to give altitude, and also permits data exchange. So it could send information back and forth between the aircraft and the appropriate receivers. Okay. Mode C or mode S transponders are mandatory, is a mandatory requirement for many busy areas of controlled airspace. All right. So mode A, just a code. Mode C, a code and altitude. Mode S, a code, an altitude, and an exchange of data. So that's where you can see call signs, the plane type, the ground speed, and all that sort. Right? How fast the plane is going. All right. We've touched on everything. Once again, please, if you have any questions, I am more than willing to stay behind, answer some questions. If not, you guys are free to go. Thank you for bearing with me. I appreciate it. I really do. I know it's Friday, but if you guys have any questions, please just let me know. I'll stick around till the last person leaves. If you want to stay here for the next hour, I'm okay with that. But thank you guys. Enjoy your weekend. Study hard. Right?
First of all, thank you for your explanation on VORs. That's been something that's been a little confusing for me. So that was great. I appreciated that.
It was confusing for me too.
I wanted to see maybe 2 questions. Do you find that when the student gets into an aircraft, it's a little bit easier to understand? And also, do you see the future of aviation including VORs?
Okay, first question, most definitely. Okay, when you're actually able to be in the aircraft, be hands-on and, you know, test things out, right? It becomes a lot easier to understand. Okay, that's where you can do here for, that's when you can do something where you can, you know, you ask the instructor to set it up for reverse sensing, then you try to fly towards that needle and you realize, I'm not getting any closer, I'm not getting closer. Then you start flying the other direction, you realize, oh, the needle's starting to come closer now, right? So you can try those things out and get that firsthand experience and, you know, make that correlation in your mind. In terms of the future of VORs, a lot of VORs are breaking down and not working and then not bothering to fix them, right? Because the advances through GPS have gotten so much better and so much more reliable that it costs a lot of money to maintain these VORs.
Right.
Right? I think it's somewhat, I forgot, I had looked it up last year, but I forgot how much it is, but I know that it costs millions of dollars to install, and then it costs another couple thousand, you know, maybe even like hundreds or tens of thousands of dollars a year to maintain, right? So a lot of VORs, they're not repairing them as they break down, but they also have so many that, okay, the ones that they still might need, they can keep those in service, but it's not going to be as much as it used to be.
Yeah, for sure.
Yeah. That's like
Okay,
NDBs, right? The NDBs, we touch on it, but we don't ever learn how to fly it because most of our aircraft don't have NDB equipment anymore. They don't have, you know, that's why I was kind of like, NDBs, you know, it's cool to know about, but you're not going to be required to learn it because we have VORs in our aircraft, we have GPS in our aircraft, right? They're not building aircraft with NDB equipment. Right.
Yeah, can you check to see if I was able to get signed in? Because I did have to log back in on Zoom earlier.
Yeah, you were signed in. It just doesn't show you signed out.
Okay, let me do that real quick.
But as far as everything else, I think everybody else showed that they signed out. Right?
Okay, am I signed out now?
Yes,
Awesome.
you're good.
Yeah, thank you for your time today.
No problem. Thank you, guys.